For the next speaker, I am pleased to welcome back to KIPAC Stefan Funk. Stefan was here from 2006 to 2014, first as a research associate here at SLAC from 2006 to 7, and then he joined the SLAC faculty from 2007 to 2014, before he moved across to the FAU University Erlangen-Nuremberg, where he is now as professor of physics, working on understanding astroparticle physics, the origin of cosmic rays, and better understanding dark matter. And Stefan is here to talk to us today about building observatories to access the high-energy universe.
Thanks. Thank you, Dan. So it's a great pleasure to be back. Thanks to the organizers for putting together a very exciting program. I've learned a lot. Like Saptarshi yesterday, I will talk to the P in KIPAC. And I don't think I have to motivate why gamma ray astronomy is an important field. I hope that you all in the audience know that this is true, but I will try to describe a little bit what we plan in going beyond the current instruments. Before I do that, I can't help but reminisce a little bit about my great time I had at KIPAC. I came in 2006 as just out of my PhD, which I did in Heidelberg, on surveying the inner part of the galaxy with the HESS instrument, a ground-based gamma ray instrument. And I came here to work on Fermilab. This was really an absolutely fantastic and amazing time. We had such a nice group of people here. We had, KIPAC was just starting up, but in addition to that, we had really a marvelous group of people working on Fermi. You see Elliot Bloom here, Persis, Roger Blandford, Roger Romani, who's in the audience, then Seth Deagle, Eduardo, Tune, of course, Peter, who was responsible for getting this whole endeavor started. And then up here, you see some of the people that worked here. It was really scientifically the most exciting time in my career. So I came, as I said, in 2006. The LAT was still here in the clean room, and it then was shipped off and launched in 2008. And then, of course, there was such a wealth of data that we had to deal with, and we had the joy of dealing with, that if you want, I could give a talk about this, but I will not. Let me just say one more thing, which I find was really exemplary in the Fermi team here. And I think this lives on in Rubin, namely the collaboration between people who work or whose background is in astrophysics and people whose background is in particle physics. We always talked about this when we were in the middle of it, doing Fermi analysis, how important this is. And we always said that we have to bring the particle physicists and the astrophysicists together. I think looking back at it now I think we really did that. There are really people who were hardcore particle physicists who talked about pulsar emission or about foregrounds for dark matter studies and all of this. And I think we really managed to bring these two communities together. And I'm very proud of this. Okay, so with this, let me move on. So this is basically this picture contains what we learned from the gamma ray sky with Fermi. This is the picture of the whole sky at GeV energies. You see lots of sources. You see very interesting features. I don't have time to go into all of this. There might be exciting unknown things still hidden in this. We're still basically exploring what the GeV sky tells us. NASA put out this thing which they claim was there are 10 most important aspects that we learned from Fermi. Of course, this is a matter of debate, but you can see some of the things. For example, we found Fermi bubbles, large-scale features perpendicular to the galactic plane that are potentially related to past activity of the supermassive black hole in the center of our galaxy. We learned a lot about the galactic center, about the emission, hadronic emission or acceleration of protons in supernova remnants. The Crab Nebula with its flares kept us busy for quite some time. AGN, GRBs, pulsars. We discovered new pulsars with blind searches. We discovered millisecond pulsars that have no radio emission. Lots of interesting astrophysics that we discovered with this. But of course, the DOE in its wisdom was not so much interested in all this astrophysics. And so I have one slide for, I know there's no one from DOE in the audience, but here at SLAC, we focused, at least in part, on dark matter searches. And if you if you look back to the early parts of the Fermi mission, basically all our dreams had come true. We discovered in the center of our galaxy emission that resembled a line at 130 GeV, exactly something that you would expect from dark matter. It turned out that this was partly an instrumental effect, partly unlucky statistics. So this went away. And here, again, it was tremendously helpful that we at SLAC had such great knowledge in understanding the instrument, because we built the instrument. So we were very much involved in the understanding of this signal, of this potential signal, and addressing its systematics. The other dream come true was that we found enhanced emission from the galactic center, which we could not really explain with all this pesky astrophysics that I was talking about before. That could also be a dark matter signal. This signal is still there. And there have been lots and lots of papers written about this, whether there's a previously unknown population of millisecond pulsars that could explain it, whether it's really dark matter. And I would say the verdict is still open. But what is definitely true is that looking at dwarf spheroidal galaxies, which we didn't detect, we put very stringent upper limits on WIMP dark matter scenarios. Here, the annihilation into BB bar. Here, the annihilation into tau plus, tau minus. And you see that if we compare our limits here in the, say, 10 GeV to 100 GeV mass range with the thermal relic cross-section, you see that we basically rule out vanilla WIMP models with masses in that range. This was, of course, very important work, and it was mainly done here at KIPAC. If you look at the corresponding authors, it's maybe a bit hard to see. Andrea Albert, Keith Bechtold, Alex Durlica-Wagner, Louis Strigari, Matthew Wood, all KIPAC members. And these are the best upper limits we have so far on WIMP annihilation models. Yeah? So I think partly we've also fulfilled this requirement from DOE to work on dark matter. Okay, but this talk is not about Fermi, it's about the future. And if you think about the future, it's very hard to build anything that is better than Fermi and launch it. So the focus of the community is turning to improving observatories on the ground. And the idea is very simple. You have a very high energy gamma ray entering the atmosphere. You generate a particle shower consisting of electrons and positrons, just like in your particle detector, an electromagnetic shower. The particles in this shower move faster than the speed of light. So they emit Cherenkov light, blue optical light that you can detect with large telescopes. And this is one way of doing it. And the other way of doing it is to detect the particles themselves. You can put up large water tanks or something like this and detect the terrain of light of these particles in the water tanks. And these two ways are both pursued for the future, as I will try to explain to you in a minute. Just to say that on the ground, you really do things that are important and are an important complement to the Fermi sky that I just showed you. This is an image taken by the LASSO experiment in China. They have an array of water tanks to detect the particles themselves, as I mentioned just before. And this is the sky as they see it. This is a so-called significance map above 25 TeV, so way higher than the Fermi map. Again, it looks a little bit different to Fermi. You don't see much galactic diffuse emission, but you see individual sources. Many of these sources are associated with energetic pulsars. And this is, of course, happening now, and it's a very nice complement to what we have been doing with Fermi. The problem is a little bit that most of the activities currently have been focused on the Northern Hemisphere. So LASSO, this experiment that I just described, is in the Northern Hemisphere. HAWK, another one, is in Mexico, also in the Northern Hemisphere. Then there are these Cherenkov telescopes, Maragik and Veritas, also in the Northern Hemisphere. And basically only HESS is operating in the Southern Hemisphere. And this is something we want to change. And so the future plans call for 2 observatories that we're going to build. One CTA, you've heard me talk about this a long time and a lot. And the other one is SWGO, which is an array of water tanks that we are planning to build in the Southern Hemisphere. And I will talk now about both of these. So CTA, I don't think I have to explain much about this, is an array of Cherenkov telescopes that we will build. The main array in Chile. I'll show you in a minute where the site is. There is also a Northern Hemisphere array, a smaller one on the island of La Palma that is being built. So we built them different size telescopes. I'll explain that in a minute. Large size telescopes, mid-size telescopes, small size telescopes, and the combination of those give you access to a large energy range. We have about 25 countries, 1,250 members, and many of the former LAT team members are, of course, now also members of CTA. This is a rendering, what eventually the array will look like. So you see that you have different size telescopes that I just mentioned. This gives you access from about 20 GeV to about 300 TeV gamma ray energies. And as I said, we will build this in 2 locations, so we have access to the whole sky in the future. If you think about how you build such a Cherenkov telescope, basically, as I mentioned, you detect the optical Cherenkov light of the particle shower generated in the atmosphere by the incoming gamma ray. The trick, this shower doesn't produce a lot of optical light, bluish light, by the way. The problem is, of course, that even if you observe in a moonless night, there's still a lot of optical light around. So you have to somehow suppress this optical light. And the trick is that this optical light arrives in very short bunches of, say, 10 to 100 nanoseconds. So what you want is a camera that can take 10 or 100 nanosecond exposures. Just to show you how this looks like, this is if you put a shower in the atmosphere with its Cherenkov light, plus the typical night sky background, and you take exposure of 3 milliseconds, this is what a camera would see. So it's hard to pick up the shower here. And now I'm going down in exposure by factors of 10. So this is taking 320 microsecond exposure, 32 microsecond exposure, 3.2 microsecond exposure, And this is basically the range, 300 nanoseconds or even a bit shorter, where we want to be. And then you clearly see the shower. Yeah? And this is, by the way, the only reason why our eye cannot see the shower, because it's optical light. So in principle, we should be able to look up and see showers. But of course, we cannot do 320 nanosecond exposure with our eyes. Yeah, our eyes take, I don't know, millisecond exposures. Okay, so this is the trick. This is, okay, so 32 nanoseconds is even better, yeah. Okay, so this is the trick, and we set out here in KIPAC to do this with the help of LDRD money to develop camera electronics to do this. So you see these gentlemen here who worked on this. These are boards that we developed, and they were, I mean, basically, we developed all of this in collaboration with a colleague at Hawaii, Gary Warner, who very unfortunately died this year of cancer. But his memory lives on, and our work that was started here at SLAC lives on, because basically the majority of all the cameras that we build will be used in CTA will actually use this chip and this electronics. Yeah. So if you look at the Southern Array, for example, you see here the positions of the different telescopes, the large-sized telescopes in the middle, in dark blue, the mid-sized telescopes around, and then in light blue, the small-sized telescopes. And in particular, these small-sized telescopes will all use this electronics that we started here at KIPAC. Okay. Okay, thanks. CTA will be built in Chile at a site located between Cerro Paranal, where the very large telescope is, and Cerro Amazonas, where the EELT is being built. So at a high plateau there, this is what it looks like. This is what it currently looks like. So we now have, so here's a road running through this high plateau, and here's an access road to where the array eventually will be. And this access road is being built as we speak. And so this is the status. And we hope to put the first telescope to the southern side next year. The northern side in La Palma is a little bit further. This is a rendering, unfortunately. So this is not what it looks like right now. In fact, this is what it looks like right now. So one telescope, a large-sized telescope, is already built. They are taking data. This is an example of the Crab Nebula that was studied with this LST-1. They're taking spectra and publishing data. So this is clearly ongoing, and they are, of course, in the process of building the additional telescopes there. And this eventually will be what the galactic plane will look like with CTA. So we expect a much richer environment, and we expect to see many more sources, for example, compared to HESS. Okay, turning to the second part, the SWGO will be an array of particle detectors located at a high altitude in the southern hemisphere, and it will complement LASSO and HAWK. So basically serving the southern part of the universe at the highest energy, in particular the areas that, for example, have the galactic center, have the Fermi bubbles, all of this. Here are some of the locations we're looking at. So we're looking at a site above 4.5 kilometers in altitude, in Bolivia, in Argentina, or in Chile. It's not decided where we will go. It's also not decided yet what the water unit will actually look like. We're looking at lakes, high altitude lakes, either natural lakes or build an artificial pond, or to put tanks up like HAWK has been doing. And there are pros and cons for all of these, and we are thinking about how to best do that. Together, CTA and SWGO will really be a nice complement to the dark matter studies that we have been doing with Fermi. We will be able to reach the thermal relic density if we understand our backgrounds well, if we understand our foregrounds well, but I'm confident that this will be possible. And so with all of these, we will have full sky maps of the GeV to TeV to PeV sky. This will be super exciting. It will also be a nice complement to current and future neutrino experiments. And with this, we will basically have access to the whole energy sky with different messengers. And I expect us to be able to do studies of high energy emission in the whole universe, basically. SWGO is currently in an R&D phase. We are, this R&D phase is, we're going to complete probably by the end of next year. We're a little bit delayed by COVID. Then we move into a prep phase, and full construction could start in 2026. There was a recommendation by the decadal survey that the US should be involved at the level of 20 million, basically based on the heritage from the Hawk experiment. I think this is a very good idea. And so this brings me to my summary. I think current experiments are still providing meaningful results, particularly also Fermi, of course. It's central to it's a central element to the landscape of multi-messenger astronomy. And the prospects are very good for the next 5 to 10 years. And before I end, I again want to come back to a personal note. Well, okay, so first a personal, maybe negative note. I know that the US is probably not going to be involved in CTA. And I do consider this as a professional failure, that I and we here didn't manage to convince the US funding agencies to get involved. On the other hand, something I'm really proud of is this picture. This is a compilation of postdocs and graduate students who worked with us here in the Fermi group in KIPAC over the years. And these are the people, they all have faculty positions now. Yeah. I tried to look up what percentage of Fermi people that is that worked here that now have faculty positions. It's certainly way higher than 50%. And this is something I'm really proud of. And I know all of these people are proud of having been here in this wonderful and fantastic environment. They carry their KIPAC heritage into the world. This is really something I think we all in KIPAC can be proud of. And so with this, I stop here. I thank you all, and happy birthday, KIPAC.
Okay, thank you, Stefan, for that wonderful talk. Any questions? Yes, Paul.
What are the trade-offs between the small and the large telescopes at CTA?
Okay, so if I had infinite money, I would make them all large. Unfortunately, I don't have that, so I have to find a balance. You want both small and large-sized telescopes to cover a large energy range. The small-sized telescopes, basically, you can spread them far and get area, yeah, at relatively low cost. The large-sized telescopes, you need them to be large to be able to detect faint showers at low energies. And then it's basically a trade-off of getting enough sensitivity at low energies and getting enough sensitivity at high energies. And this is how we came up with the numbers.
If I could ask a kind of related question, I guess, to that. I was interested in the trade-offs between the Cherenkov and the water tank design, and if there's one or other of those are better suited to different science cases, or if all the science cases benefit from having both.
Well, the trade-offs are that it turns out that the Cherenkov telescopes have better angular and energy resolution. So basically you can resolve the features or determine the features of the shower in a better way. The trade-off is that you need darkness. So the ground-based arrays or the water Cherenkov telescope arrays, they can measure 100% of the time. And the instantaneous sensitivity of the Cherenkov telescopes is much better. So basically, you can say the water Cherenkov is more like a survey instrument, and the Cherenkov telescopes give you the detailed information about individual sources. So it's like the vertical integration Rob was talking about if you have the combination of both.
Great, thank you. Tom, up at the back.
Well, it's just so great to have you back, Stefan.
Thanks, Tom.
Let me ask you quickly. I mean, you may have said this, but I'm curious more about the data rates and sort of the data handling challenges. And what is, what could you imagine, progress could be in helping you analyze that data?
Do you mean for CTA, I assume? Yes. Yeah. Okay, so data rates are small compared to Rubin. But still, of course, substantial. So I don't have the number at the top of my head, but I think if I remember correctly, the raw data is about a factor 10 below Rubin. We will, of course, do some on-site processing to reduce that data rate further before we ship the data to Europe or wherever, to data centers. What is certainly something we're looking at very heavily, like everyone, is using artificial intelligence to separate gamma ray initiated showers from hadron initiated showers. So, I mean, we're using graph neural networks because we have sparse data rates. There's a lot we can talk about, but machine learning is certainly be used for background rejection. We're also starting to use it for the reconstruction of the shower properties. But this is clearly something that is only starting, and we're learning a lot from our colleagues at the LHC. I would say they are, I don't know, 5 years ahead of us, certainly in this game, and we're learning a lot from them.
And Steve, and then Greg.
Yeah, thank you for that fantastic talk. And just to say that the record of success for the younger people who work with Fermi is absolutely amazing. And your leadership is part of the reason for that.
Thanks.
When you think of Fermi and you picture the eventual successor to Fermi that will fly, what do you picture?
Oof. Yeah, so this is hard. I think, so Fermi, to me, was, of course, as always, a trade-off between area of the instrument to basically, effective area on the one hand, and precision on the other hand. And I think that if you really think about going beyond and doing a factor of 10, I don't think there's much you can do with area unless you build, I don't know, there were plans of putting Fermis on the moon or something like this, or in orbit, but a fleet of Fermis. But I consider, if you really want to go that route, I consider precision the better direction. And then you would want to build something that has a better angular resolution. And I think you could design your tracker in a way that you increase the precision and at the expense of area. That's where I would go.
And Greg.
About these guys again.
Stefan, maybe you could comment on using the Cherenkov telescope array type telescopes for very high angular resolution optical studies. I think that that's sort of a new and very exciting area.
Yes. Okay, so so this is a very old idea that you could use light buckets to do intensity interferometry. Goes back to Hanbury, Brown, and Twiss, who built a system of 2 telescopes, large optical telescopes on rails, so they could change the separation between them, and had 1 PMT in the focus. And basically, you can correlate the arrival time of photons from a source in these 2 telescopes. And this worked. They did measurements with their electronics from the 1970s. And with that, they were able to study the angular extent of bright stars at the sub-milli or at the milliarc second level. Now, this field basically got dormant at the expense of amplitude interferometry, which is what people are doing in the optical, or have been doing in the optical. The problem is that the amplitude interferometry gets harder and harder as you increase your baselines. And so this is why people go back and start to think about using these Cherenkov telescopes in times when the moon is very bright, and we typically don't do gamma ray observations for exactly this purpose. And people are doing this now in MAGIC and Veritas and HESS regularly. And of course, electronics and everything has moved on, so we can do much, much better than Hanbury, Brown, and Twiss. This is certainly something like a side use people are considering. And it's basically working. I mean, the existing instruments show that it works. And this is also something we are thinking about for CTA. Absolutely.
Let me just follow up.
Yeah.
With CTA, how bright is that?
Yeah, okay. So I think I heard different estimates, but I think what I heard recently is you can go down to magnitude 8 or so, 8 or 9 or something like this. Depends, of course, on how long you want to observe and all of these things, but it's brighter objects.
All right, thanks.
Okay, well, let's thank Stefan again for that wonderful talk.
Thank you.